morning, everyone. Good morning, Zurab in particular. Thank you for being with us again. Good morning to all the participants. So today is the last lecture. Yeah, it's the last lecture of the cycle on mathematical proofs with Python by Professor Zurab Janelidze. So Zurab, I think everybody should know you by now. so I simply hand over to you. Thank you very much.
Thank you very much. So we're going to continue from where we left off yesterday, which was in the middle of somewhere, and that somewhere was this geometry proof. But since it was in the middle, it might be a good idea to restart. So I'm going to copy this code, and we're going to go line by line and more slowly now that we have more time. And I'm sure we will be able to get to the end soon enough. So I'm opening here my Spider. And I'm going to hide some of the lines so that we can go through it indeed line by line. And please, if you have any questions, interrupt and ask, especially that it's not so many of us this morning here. Okay, so just to remind you that we are working from these lecture notes, which now has a new section, section 9, and that's where we are. And we're now doing the last activity of section 9. So I copy pasted that code from the lecture notes and I compiled it, and let's see what is the output. We've got an axiom, which we're going to use for proving a certain theorem. The axiom, as you see, is long, but we can go step by step and try to understand it. So you see here that the axiom has an opening bracket, which is matched by a closing bracket at the very end of the axiom. That means that this entire thing is just one statement. And so since it's one statement, we expect that inside that statement will be a formula, and indeed, this column here reveals the existence of such a formula. And however, if I look at what is on the right side of the column, I see that the brackets are not complete yet. There is one more set of brackets here, which kind of shows me some part of that formula, right? So let's try to read what's inside that statement. So we have a plane P. So we've got a P that's a plane, and if we have, you see, then there is a column after that. So if we have a plane P, then, so this column, remember, that represents then we will have A, we will have B, we will have C, where A and B are not equal to each other. A and C are not equal to each other. This is something we discussed the previous lecture, right? When we have implying false means that they're not equal. And let me also remind you quickly that this formula here represents fallacy, instead, in other words, falsity. Okay, so let's continue reading this. So A and B are not equal, A and C are not equal, B and C are not equal. Furthermore, A is a point, B is a point, C is a point, A lies on P, B lies on P, C lies on P. So at this point we have what? We were given a plane P, and then the axiom claims that whenever we have a plane, so it's a flat surface that's infinite in all directions in usual Euclidean geometry. On that plane, you will have certain points, A, B, C. You will definitely have these points. That's what the axiom says. And not only these 3 points lie on this plane, and not only they're not equal to each other, but moreover, we also are given this fact about them, which says that if there was a line L, right? So if we have L, that's a line. such that the point A lies on L, the point B lies on L, and the point C lies on L, then this would imply fallacy. In other words, such a line cannot exist. So just to give an illustration of this one more time, we did it already yesterday. So the axiom says that whatever plane we have, we will always be able to find 3 points there, A, B, and C, such that it will not be possible to find a line, a straight line, right, that passes through all 3 of them. So whenever we try to make a line from our usual spatial intuition, we see that the line will only pass through 2 of these 3 points, not all 3 of them. So I need existence of such points. Of course, I can draw 3 points in such a way that one line passes through all 3 of them, but the point is that we are saying that it is possible to draw 3 points in such a way that the line, that no line can pass through all 3 of them. Okay, so that's what the axiom says. Now, in fact, the proof that comes after, it doesn't really require the knowledge that the points A, B, and C are different from each other. So to simplify later on reading the proof and writing it, let's remove that part from the axiom. So I'm going to remove those pieces which say that the points are distinct from each other, just for later simplicity. Of course, having extra information about these points doesn't really do a harm, but of course, also knowing that we don't need this extra information for our purposes is useful. So I've now compiled the same axiom without that extra part, and it becomes a bit shorter. Okay, our goal is to prove.
Sorry, Zurab?
Yes, please.
Yeah, is it not kind of important that the points are distinct?
So the reason why it's actually not important is that if they were not distinct, if 2 of them were equal to each other, we would actually be able to find the line passing through them. But remember, we are saying that the line cannot pass through them. So the fact that the line cannot pass through them will imply that they must be distinct.
Distinct, yeah, sure.
But of course, this will only be true in the case when we have an additional axiom saying that for any 2 points, there is a line passing through them. We don't have this axiom here. So for these purposes, for the theorem, where we're just trying to find 1 point outside the line, it turns out it's not important that they're not distinct.
Yeah.
Yeah. Okay. But thank you very much for that question, and feel free indeed to interrupt and ask anytime. It's last lecture, so it's important that we understand everything. So I would prefer that we do less and we make sure everything is clear than rushing through something and skipping and so on. Okay, so that's our axiom. And then the theorem we want to prove is that if I have already a line on a plane, outside that line, on the same plane, I will be able to find a point. So the theorem will say that if I have a plane and a line on it, so plane P, line L, it is always possible to find a point on the plane which is outside the line. Now, as we said yesterday, it's actually very easy to see why this is so, because we know that by the axiom that there will be 3 points, and certainly it will not be the case that all 3 points will lie on that line, because we said that these 3 points cannot lie on the same line. So then at least one must be outside it. Now, this argument, which seems intuitively obvious, it still needs computational verification, in other words, a proof. And the reason why we choose obvious things to prove in the beginning is because if we can't prove obvious things, then we will not be able to prove even more difficult ones. And as you see, the proof of this even obvious, something that appears to be obvious, is not so obvious at all. And this is a phenomenon that suggests that there is a lot of mathematics that our brain can do subconsciously. And that's a very interesting phenomenon. The other thing I should say here, of course, is that when we say that out of these 3 points, one definitely will lie outside the line. If we want to be a bit more precise, we could start considering cases, right? Case 1, where A and B lie on L, then C must not lie on L, because otherwise all 3 will lie on L. Then case 2, when B and C lie on L, and so on, right? So this consideration of cases, if I start writing it out, it will start get longer. What is interesting about this proof is that it doesn't require consideration of cases. Okay, so let's look into the proof. Also, another reason why we chose a proof like this is to showcase the axioms that deal with falsity. And after completing this proof in this course, we would have showcased all the deduction steps that are needed for establishing any kind of mathematical truth. And it's also quite remarkable that by such very simple examples of intuitively obvious theorems and through their proofs, we're able to really have the full list of all the rules that are needed for establishing, no matter how complicated mathematical, and hence also all scientific facts that can be confirmed fully by the method of proof. Okay. The proof of this theorem just has one line so far. I've removed all the other lines because we're going to do that step by step. And the only line it has is an assumption. So if we look at this line, the first line, it says that we have L, we have P. We know that L is a line. We know that P is a plane. And we know that L lies on P. So that's exactly this initial data before we say that the point must exist. We want to prove now that the point must exist outside the line lying on P, right? So we're going to assume that we have a line lying on P, and the hope is that eventually after some steps, we will come to the conclusion that there exists a point that does not lie on L, but lies on P. Great. Now, just to remark and remind you one more time, the reason why at this point Sophia formulates theorem as empty statement is because in the proof we are in assumption depth 1. So this is an assumption. We haven't stepped out from that assumption yet. You can think of this as kind of obstacle for that. So if we have this vertical line, it means that we are not yet outside our any of the assumptions. Sorry, this vertical line means that we are inside a certain assumption, right? And you can intuitively think of it like this: assumption is something I'm thinking before I tell my thoughts to somebody else. So while I'm thinking, I'm not going to be necessarily. I mean, I have to first think, and then after I complete thinking, I need to say the result of my thinking, right? So when we have a bracket like this, the vertical line or the double line, it means that I'm in the thinking process. And so that's how Sophia interprets this. And she says, okay, you're still thinking, so you haven't told me anything yet. And hence the output is an empty theorem. Okay, now if I had to, instead of going with the intended line, do a synopsis here, which means stepping out of that assumption, you see what will happen. So that vertical line changed to this block, and that block refers to the fact that I've assumed that thing and then concluded nothing from it. But in other words, then Sophia interprets this as concluding itself from it. And so the next line, which now steps out from that thinking process, now this is a statement that Sophia will consider as a message to her, says, assuming this thing, we can conclude exactly the same thing. And then Sophia puts that as a theorem. So this is just to remind you one more time that what Sophia shows us here is how she interprets what we have proved and not what we wanted to prove. And this is good because if what she shows us here at the end, right, will match with what we wanted to prove, it means that our proof is correct. So this is how she helps us with the proof. She verifies the proof for us in that way. So I'm proving something. She will, of course, she will never allow us to make an illegal step. That's another thing. I'm proving something. I can never make illegal steps. If I do something illegal, then Sophia just will enter an empty statement in that line. And when I'm done, I'm going to look how she perceived what I proved, and I'm going to see if that matches with what I wanted to prove. And if it does, it means that my proof for what I wanted to prove is correct. Okay. So at this point, this is not what I wanted to prove, right? I wanted to produce a point, and that's not the case. So we then try something else. Okay, so we've assumed that we have a line and a plane, and in the next line, let's see what we do. In the next line, we are recalling the axiom. You see, it says recalling I2. I2 is exactly this axiom we already spoke about. So there is no need to go through this line because it's supposed to be exactly the same as this. However, we notice something very interesting. We notice that the P, the symbol P here on this side has been replaced with P prime. Why is that? Well, we already discussed this type of phenomenon yesterday. The thing is that in our proof, we already have a certain P. So this variable P is already reserved. It's used for something. And now imagine maybe you're applying your mathematics to chemistry, and you have some computations with some variables, and now you want to use some theorem from a book, and you go to the book and you copy paste your theorem, but that theorem was phrased using the same variables as you've already encountered in your work. And now you don't want these variables to be the same because they don't have to be the same, right? So when you will copy paste the theorem from the book, you will change the names of variables so that there's no clash between the variables coming from the book and the variables you already had for a completely different purpose. So that's exactly what Sophia is doing here. She's renaming that P to P prime because this P that we have here, the scope of this P will include also the second statement. And because it includes the second statement, there will be a clash of interpretation between that P and the P that we borrowed from the axiom. And the same happens with the line, because we had already a line in the first, a line L. This is not number 1, by the way. This is line L, symbol L, and we already had L, so she had to rename L to L prime. Now, in the next line of proof, if we look at the explanation of what line 3 does, it's application of line 2, and it says in brackets with concretization P. Oops, sorry. So what does that mean? Going back to the axiom, right here, the axiom says that for every plane, something will happen. Namely, 3 points will lie on it, right? Which are such and such. So this P here could have arbitrary value. Did anyone say anything? The P here could be anything. So this axiom could be applied to any plane we like. And we actually want to apply that axiom to the plane that we're given. So initially we said that we need to have a different variable P prime here, not to clash with the other one, but we actually want this axiom for that specific P that we're already given. So that's what we're doing in the third line. We're asking Sophia to apply this axiom in the case when the P prime from the axiom is our P, the one that we're working with in the first line. And so if you look at this deduction, this .d deduction rule, which we already looked at in previous lectures, it applies the statement at line 2 and then gives the coordinates of how should P prime be interpreted. Coordinates is 1, 2, that means first line, which is this line, and then second statement, which is P. And in brackets here, she reminds us what we did, that we did it's called concretization because we've got an abstract P prime here. We're saying something will be true for abstract P prime, which any P prime, but now we want to apply it for a concrete P, the one that we have in line 1. And so in the third line, we now know, after applying the axiom to our plane, that there are 3 points, A prime, B prime, C prime, lying on this very plane P that we have in the first line. So you see, it says, well, first of all, it says A prime is a point. Oops, sorry. There we go. A prime is a point, B prime is a point, C prime is a point, and then A is in B, A lies in B, B lies in B, A prime lies in P, B prime lies in P, and C prime lies in P. And finally, we also know that this long statement which says that there is no line which will pass through all 3 of them. I think this might be a good step where if you have any questions, if you're not sure of anything so far, you could ask. Then we can continue after.
It doesn't seem like there is any reaction. Zurab.
Okay. Yeah. So maybe I can ask, is everyone okay? Are you following what we're doing? Well, because if you're not following, then we have to definitely
now there is a thumbs up, or a few thumbs up, Zurab.
Okay, wonderful. Thank you very much.
So I think we are fine.
Okay. Let's look at the next line. On the side of the code, we see here that this will be an assumption, right? Because we have dot A. And what does it say? What does the assumption say? It assumes there is a D that's a point that lines on P. No, not quite, because then there is a colon, right? So I have to think of this whole thing implying that thing. So every time we have a D that's a point that's on plane P, we will for sure conclude that D also lies on L. So it basically says that every point of the plane lies on L. We don't want this to be true, right? We want to find a point on the plane that does not lie on L. But now we're assuming that every point on the plane lies on L. Why are we doing that? Would someone like to answer this question? If we want to find a point that does not lie on L, why would we be assuming that every point of the plane lies on L? You can put your answers in the chat or speak them out.
I just want to make an attempt.
Mm-hmm.
It's because we can use that and then use the what is it, the fallacy of it, so that we can make use of the the fallacy probably.
Okay, so I think what you're saying is that we will derive a contradiction from this, and hence conclude that it's not true.
Yeah, something like that.
Okay. So we'll see. So if I assume, okay, let's first run this. So when I run this, you see that now there is another gadget like we had before, right at the beginning of the proof. This indicates a new assumption has been introduced. So our assumption depth at this point now is 2, because there is one assumption depth coming from the very first line, and then the second one which has been just introduced. And at this stage, we are assuming that every point that lies on P also lies on L. Okay, let's see what we can do with this. Well, in the previous line, we already have 3 points that we certainly know that are points, first of all, and that they lie on P. You see, we have A prime lying on P, B prime, and C prime also lying on P. If we assume that every point lying on P must lie on L, then these 3 points will also lie on L. Yeah? So we can apply this line 4, in the case when D is concretized to A prime, to get that A prime lies on P. So let's do that. Sorry, not on P, on L, right? Because A prime, we knew lies on P from the third line, and hence we can conclude by this assumption that it lies on line L. There we go. And if I look into the code of this, we have here, again, this .d rule, which is the one that allows me to apply implications. 4 refers to the location of the implication that is being applied. And then these are 3, 1 are the coordinates of the concretization. So concretization happens with A prime. It means that this free variable d, the variable where we have freedom to select what value to give to it, right? We want to give to it the value A prime. That's what this means. And the coordinates of A prime is 3, 1 because, so it's 3, 1 because it's on line 3. You see, this is line 3, and it's the first statement on line 3. Now, in the same way, we can get the other 2 points also lying on L. So we now have A prime lying on L, B prime lying on L, and C prime lying on L. But remember what we said here. We said here that having a line, having L, that's L prime, that's a line, and such that A prime lies on L, B prime lies on L, and C prime lies on L, all of that implies fallacy. So that's wrong, in other words, no? But this is exactly what we have now. We have line L, this is our line L, and A prime lies on L, B prime lies on L, C prime lies on L, right? So by this then, we must be able to conclude fallacy. How? Well, it's an implication, and we apply implication with this .d rule. The only variable to concretize here is L prime. And we want to concretize L prime to be L, right? Because that's what we have here, L. So the coordinates of L are 1, 1, and hence the next line is this. Something happened there. Let me check what happened. Okay. I think one parameter is wrong there. Let's see what parameter is wrong. I know what is wrong. Remember, we deleted some parts of the axiom which we said we don't need. But it's actually good to also discuss error handling here. So Sophia didn't do what we wanted her to do, right? I mean, at least what we expected she would do. Instead of giving us fallacy, she gave us empty statement. And she says application is void. What does that mean? That means that when you see something like that, that means that we didn't do something right. And now we look carefully at the parameters. Number 3 refers to line 3. This is line 3, and this is exactly where the thing we're applying resides, okay? Then this parameter here is a list of concretizations, but we only have one concretization, L prime concretized to L, and the coordinates of L, as we already said, is 1, 1. So that's fine. And then we have this 13 here, which is the position of the implication we're applying. So it's the position of this. Is the position of that 13? Let's count. Position of 1, 2, 3. This would be position 4, 5, 6, 7, 8, 9, 10. Aha, it's not 13. Position is 10. And the reason why it's 10 and before it was 13 is because we deleted 3 things basically, right? The statement saying that every 2 points are not equal to each other. Remember, we deleted that. So then we have to put 10 here instead of 13, and then it should work. And it doesn't work indeed. Okay, so we deduced fallacy from the assumption that every point lying on P also lies on L. That's good. Now we can step out from this assumption. Do synopsis, this .s rule. And you see, in this line, in line 8, assumption depth was 2, that we see by this double vertical double line and this one. But now we've stepped out of the assumption, and assumption depth is back to 1. Now, what does the conclusion say? It says that this thing here, that the thing I'm highlighting, implies fallacy. In other words, that thing is false. So it says this thing is false. What is false? It's false that every point of P must lie on L. This brings us very close to what we want. Remember, we want to prove that there is a point in P that does not lie on L. And so far, we've established that it's false that every point of P lies on L. So surely this should take us close to proving that there actually exists a point not lying on L, right? Now, in real life, if you imagine you are in a room with people, surely wearing masks, otherwise you might get COVID like I, even though I did wear masks. So you're in a room with people, and you know for sure that not everybody in this room likes ice cream. That doesn't necessarily mean that you know who doesn't like ice cream, right? You have to investigate still. Huh? So knowing that not everybody in a certain group has some property doesn't mean that you immediately have the member of the group who does not have that property, right? So something of this kind is happening here. For now, we know that not every point on P lies in L, but what we want to prove is that there is a point in P lying on L. So we actually want to be able to state the existence of that point explicitly, okay? So let's try to write down how this is actually different to what we really want to prove, to make this. So this is where we kind of stopped last time, and then we rushed through a little bit, and so we now want to understand very well how this is different from what we actually want before we proceed with the proof. So I'm going to write out both what we obtained and what we want to prove. We obtained that we obtained this basically. So having a D, that's a point. That lies in P. That implying that the same D lies in L. So that whole thing must imply fallacy. Right. So in other words, in words, if we write this in words, it says every point of P is in L is false. That's what we have obtained so far. What we want to obtain is there is a point of P that does not lie in L, or rather that is not in L, just to make it shorter. Okay, let's see how we will write this, the third line in the Sophia syntax. I want to say there is that something exists, right? So that is claiming existence of something, and as we've already know, this is statement that will include that thing. So I want to state existence of some D, which is supposed to be a point. So D is a point. So I'm stating that there exists a point. I'm also stating that that point lies on P. And then I'm stating that the same point does not lie in L. So would you like to give it a try on the chat? How to do that? I see that there is a request on chat, Francesco. Did you already let Elisep in? Did you see this request in the chat?
Sorry. I didn't look at the participants list. I didn't see it. Sorry for that. So thank you. Sorry. I was just looking at your slides and I didn't see the request to be admitted. They are in now. Yeah. Okay,
great. Thank you.
Sorry. My mistake.
No. Thank you. So let's type in the chat. Please type in the chat if you don't worry if it is not correct. You can just give it a try. How to say this last part, that the P does not lie on L in Sophia. So I want to make a statement here that will say P does not lie on L. How to do that? Not P, sorry. P is the name of the plane, right? The D does not lie in L. So maybe I should introduce this D already in here. So there is a point D of P, right? Such that D does not lie on L. Such that D is not in L. So how to say this part, D is not in L? We already said that there is a point D on P, but now we want to say D is not in L, this part. How to say that? Very good. There is one tiny, well, actually two tiny mistakes in the proposal on the chat. Does anyone know how we can fix that? So let me copy it here. Maybe I use a different color to distinguish from the rest of the text. So this is what we received in chat. And this is very good because it kind of captures the idea. We should say that D lying on L implies false. That's how we say something is not true. But in mathematics, definition of something being not true is that that thing implies false. Okay? That's how we break down the idea of something not being true in more a basic mathematical logical step. And then we also have a correction to this. So what was missing here was that stating these. So you see, without that, if I just think of it like this, Sophia does not then interpret this being separate from that. For her, if you look at ontology of this, for her, this whole thing would be just one formula, right? We want to separate them somehow. And not only that, not only we want to separate, we also want to say that claiming D lying on L to be true should give us falsity, not just consideration of D lying on L. Remember, there is a difference between we claim something to be true and we just think of some idea which we don't know yet if it's true or not. So when we have a formula, it's just in the thinking space, and when we are certain that we want to propose, okay, this must be correct. And this is when we turn a formula into a statement by putting these brackets, hence by stating it. So now we've got what we have. This is where we want to end up with. We want Sophia in the end to, when we finish this proof, we want her to put that line right here as a theorem. Well, I mean, it will have assumptions of L being, I mean, so it will have, under all these assumptions, we want this to hold, right? But what we've proved so far up to line is not that quite, yeah? We proved the top one. And the difference between this very top formula and the last formula is evident in several different ways. Well, firstly, even if you rewrite it in words, they are slightly different. You see? The first one says that it's not the case that all the points of P lie on L. The second one says there is actually a point that does not lie on L. And as I said before, intuitively, you can think of this difference as the difference that knowing that some property does not hold for all the things in the group, and finding someone for whom the property doesn't hold are two slightly different things. But of course, logically, they're supposed to be the same. If I know that not everybody if I know that not all of my friends are French, then I should be able definitely to find at least one friend that's not French, right? So there should be a logical way of coming to that conclusion that such a point exists from what we have already proved. So it should be logically possible to derive from there to derive this. And that's what we're going to do next. Now, so that's one difference. There's this kind of difference that's already captured at the level of intuition here. But there is also another difference, namely that the Sophia formulas are different, right? So if you look at the, I mean, they have some similarities, but if you look at the ontology, so we have this whole thing grouped together here, that implying false, whereas right here, we have this whole thing grouped together. It's almost like switching brackets, right? So you see, we have this part, and then we have colon and that, and colon and another thing. And so we're now switching brackets from putting a bracket here, basically, like this, huh? To get this. I can also write this out in usual mathematical symbolism. So think of existence of D being a point lying on P as some single statement alpha. Then I have alpha implies this is beta. Think of this whole thing as beta. And then think of falsity as gamma. Whereas here, we're saying the same alpha on this side. And this is mathematical symbol for and. Beta implies gamma. Now, if I know that alpha implying beta implies gamma, I will not necessarily know that alpha is true. So we can't generalize it so much. So this rule in general in logic would fail. Why is it the case that it holds for us now then? Well, because this alpha includes a free variable D. Okay, maybe that was confusing. Sorry about that. I was hoping that we would get something that's even at more abstract level can be established. Okay, let's see how we can derive now the thing we want to derive from what we have. Let's go back to here. So the next line in the proof, let's see what it says. The next line in the proof is an assumption. If I read this whole thing, I recognize there this part, which is exactly what I want to prove. Let me show you. So you see, having a point, having D, that's a point that lies on P, and having the fact that D lying on L is false. That's exactly what we have here. Having D, that's a point lying on P, and having the fact that D lying on L is false. Now the assumption says this thing is false. So we want to prove this, and we're going to assume it's false and get a contradiction, and hence conclude that it must have been correct. So this is again a proof by contradiction. Okay, so let's see how we can derive a contradiction from this. Another assumption comes in. This is when this gets a bit complicated mathematically. What does this assumption say? It says that there is a point D prime that lies on P. Why are we making this assumption? It's not clear at this point. If I'm trying to discover the proof, let's say I don't have already a prepared proof that I'm trying to discover, it would take a while, okay? Unless I know very well a mathematical logic. If I know mathematical logic very well, then I can derive the idea of what needs to be done here from something called Boolean algebra laws. So these are laws that relate different rules of logic with each other. So I'm not telling you about these laws. In fact, these laws are implemented in Sophia. What we're doing are these laws. So at this stage, if you're wondering why this step, I'm not going to answer that question, because I took 20 minutes or half an hour for me to figure out that this should have been the next step, and then the knowledge I used falls outside the scope of what we're doing in these lectures. On the other hand, we can also think about it like this. Well, what else could we do? I want to derive some kind of contradiction from line 10, and all I have is line 9. And line 9 tells me that existence of a point that lies on P. It tells me that every time I have a point lying on P, implying that it lies on L, is that thing is false. So somehow this part, right, is kind of almost like common part to line 9 and line 10. Yes. So now I'm thinking very, very computationally, forgetting about the meaning of things and just looking at symbolic patterns there. I see that this part is common to both lines. Line 10 has that part, and line 9 has that part, right? How line 9 and 10 are different is what comes after. And so, not knowing what else to do, I just take this common part and see what happens if I assume it. We can also think of, I mean, very often in mathematical calculations, that's what you do. You just observe some patterns and you try to see where the calculation will take you. Okay. Now we are assuming that this D prime lying on L is false. Why are we doing that? Let's see. I have here, you see what I have here? I have D being a point and lying on P, and at the same time, D prime lying on L being false. So I know that if I assume these two things together, I should be able to get a contradiction, right? So maybe that's why. Maybe I want to make use of line 10. Let's move to the next line. Indeed, that's what I did here. We are applying now line 10. So we are applying this with concretization D prime. So this D prime is a point I assume that we've got at hand, and we applied this assumption we made to that D prime. And the assumption was telling us that if I have a point that lies on P, and if I know that the point does not lie on L, then all of that must be false. That's what we wanted to prove, but we're now assuming in line 10. Remember, we're assuming in line 10 it's false, so we can derive contradiction from it. And then we step out from that assumption. And so we got that D prime lying on L being false is false. And now it becomes a bit more clear what we're doing computationally. So I wanted kind of to separate. I mean, remember the difference between line 9 and 10 is this part, and I kind of separated this on its own. You see. Okay. So at this stage, I know that if I assume that I have a point that lies on P, then I will know that that point lying on L being false is false. Next step, we recall the double negation rule. So according to the double negation rule, having a point lying on L being false, so double negation will give that point lying on L. That's exactly what we did here. We established that having a point lying in L being false is false, right? So by the double negation rule, we can conclude that this point is in L. There we go. Okay. What's next? Well, we now step out from that block. We now have that. So this is where we introduce the assumption that D prime is a point lying on P, and we managed to prove that under that assumption, D prime will also lie in L. So we actually proved here, we proved what in line 9, we said it can't be true. And at this stage, it becomes fully clear what's actually going on here. So once in line 10, I assumed that what I wanted to have is wrong. To get a contradiction, I was aiming to disprove line 9. I was aiming to get to the point where this thing, instead of being false, which is what is claimed in line 9, it would actually be true. And I managed to do that. And to do that, I would have to have assumed in line 11, I would have to have assumed that there is a point in P, and I would have to derive from there that that point lies in L. Okay, so now line 17 is in direct contradiction with line 10. Sorry, line 9, right? Line 9 says that line 17 is false. So we can use then, once again, we could then apply maybe the double negation. Let's see what happens in the proof. At this stage, what we do is it's something very simple. We simply take this line 17 and we rewrite it, replacing d prime with d. Okay. We couldn't do that before. When we introduced d prime in line 11, remember now that d prime becomes an object that exists, and it was clashing with d there. But once we stepped out from that assumption, once we stepped out from this block, and we are now here, the scope of d prime no longer reaches outside this space here. So we could as well rename d prime to d. And the reason why we are doing that is because we want this to be as close as possible to what's at line 9, so that then Sophia can identify the contradiction, okay? Because line 9 is stated in terms of d. And indeed, the next step is just to apply line 9. In line 9, okay, a question for everyone. How come with this application, we only have one parameter? In other words, we're not doing concretization. In all the other cases, when we were applying implications, we always were specifying what the free variable that we had there, what value it should obtain. But in this case, we didn't. We just told Sophia to apply line 1. And it gave us the result we expected, because as we said before, line 18 is contradicting to line 9, because according to line 9, line 18 should be false. And so we're deriving that falsity here. But how come we didn't need to do concretization? Please answer either through voice or you're in chat. There is an answer saying there is only one variable we would have to specify, but in fact, there is none. So line 9 is an implication where the left side of the implication, the right side is falsity, the left side of the implication does not have any free variables. The left side of the implication is just a statement saying something for every d. We're not applying this statement itself, we're applying a bigger one, just a simple implication. So in order for us to apply this, we just have to see that this part has already been proved, then we can conclude that part. And that's exactly what we're doing here. So there's nothing to concretize, because the left side does not contain, like here, for example, here in this implication, the left side contained a free variable d. But here, there is no free variable d. The d is inside the brackets. There is no d outside like that one. So we would have, if I have an implication like this, right? Let's say there is some beta here and some d. So this is an example of where we have a variable to concretize. But if my d is inside, like this, for example, so compare this with that, then there is nothing to concretize. In the first example, the scope of this d would reach to the right side as well. That's another way of thinking about it. Here, the scope of d lies completely within here, because it's confined with these brackets. So we have a variable to concretize when there is a variable on the left side of the implication whose scope reaches on the right side of the implication as well, which we don't in this case. Okay. So what have we achieved so far? We've began with a certain assumption on line 10, saying that what we wanted to prove is false. Remember, that's what line 10 said. Let me remind you. So we had these two things. At line 9, we established the first line of the blackboard here. And then we said, that's not what we actually want. We actually want the last line of the blackboard. To get that last line of the blackboard, we assumed it was false. That's what we did in line 10. And from that, we were able to derive a contradiction. So now we can do synapses to just state that whatever we wanted to prove being false is false. But again, double negation rule comes in here, right? So once again, we recall the double negation rule. This time we recall it for the statement we're going to apply it to. So inside this BL axiom builder, we put this parameter, which is the statement for which we want to apply the double negation rule. And we also indicate in the second parameter, we indicate in the variables, which are meant to be variables that are already have fixed meaning in our proof. Okay, and then in the line after, we simply apply the double negation rule to get exactly what we wanted to get. That there is a point d prime. So that there is d prime. That's a point that lies on P, and lying on L for that d prime is false. We're done, almost. We do synapses. We step out. We summarize what we proved, starting with the very first assumption in line 1, this one, that we have a line and a plane, right? We were able to conclude the existence of D, of a point that lies on the plane but not on a line. That's exactly what we're saying here. So what we're saying here is an implication saying that if there is a line in P where the line lies on the P, on the plane P, then there will exist a point d prime. That's a point that lies on P and does not lie on L. There is still one last step here with this dot R rule, that all it does, it just renames the d prime here into A, just to make it more beautiful, because it's not nice to have a d prime in your final theorem if we don't have a d, right? We had a necessity to introduce d prime because there was another d, inside the proof, but now we can rename it to A. So that's how this deduction rule works. Dot R, it gives me the coordinates of what needs to be so R stands for restating. So we're restating the previous line, and then it tells me when I restate them, how should I rename variables? So during restatement, you are allowed to rename variables as long as those variables are not reserved already for something else. So we're renaming L to L, P to P. We're not changing those names, but then we're renaming D prime to A. At this, is anyone who wants to ask anything? I think the microphone. Okay.
No, I just muted one participant. I think it was just a mistake. Sorry.
Okay, thanks. So at this stage, our assumption depth now is 0, right? We don't have any more this double line vertical brackets. And so we expect Sophia to display this as the theorem we proved. And if we go back to the formulation, okay, there it is. So she now says that's what we proved. And let's just confirm one more time it agrees with what we wanted to prove. This is a statement. You see it in its ontology, it consists of that statement implying the other one. And let's read this. So L, they're existing an L at the P, where L is a line, P is a plane, and L lies on P. So every time I have a plane and a line lying on it, so that existence of this L and P implies existence of a point A, right? So A, that's a point that lies on P, and the fact that it lies on L is false. In other words, the fact that it lies on L implies fallacy. Okay, any questions? So I completely realize that this is not an easy thing to comprehend for the first time, at least, right? That's why we have the lecture notes. You can come back to it anytime you like. And you can also reach me anytime you like. If you like us, if you don't understand something, you would like me to re-explain anything. But if you have questions already now, please ask. Okay, there is one here. That was, I think, from previous question. Okay. So if there are no questions on this long proof, then we're going to move into a concluding section of our series of lectures. There is one question on the chat. Is it necessary for one to understand first order logic first? So what I've explained in these lectures is basically first order logic. This is what first order logic is, except that first order logic is slightly more technical. So I've explained a slightly, so Sophia is a slightly simplified version of first order logic. However, if you don't mind, I mean, so the difficulties you encountered understanding this are natural difficulties, because this is something that people discovered after hundreds and, well, actually thousands of years, right, of thinking about mathematics, that we can find very simple common rules to all of our logical reasoning, absolutely all. I mean, by now we've covered all the deduction rules that we need to establish any kind of mathematical certainty. So you can see how powerful this is. And so it's not surprising that it was a bit of a challenge to, to understand it fully. But there is nothing new in this, in some sense, because it really relies on first order logic. The only new thing is that in first order logic, you have a bit more technicality. There are a few more concepts before you can start proving things. For example, we had this distinction between statements and formulas. There, the distinction is slightly more refined. There are some things called operators and relations, which are two different types of formulas. I mean, not two different types of formulas, but two different types of, it doesn't quite match. So I'd rather not go into comparison, because first I have to explain what first order logic is. But Sophia at her basis has first order logic. It's just slightly less technical than first order logic. But if you want to read up further, then yes, first order logic would be the further reading up that you can do. And then after you understand first order logic, you should also be able to see how the two relate to each other. But it's not necessary for one to understand first order logic first before understanding this, because what we covered was meant to be self-contained. Anyone else wants to ask anything?
I don't see any raised hands or anything.
Mm-hmm. Okay. Before starting the concluding session, let me go through Sophia.help, a summary of all the rules that we learned. So in particular, these are the proof building commands. These are the basic rules of logic that we've been using in our proof. So these are the commands we use to create every next line of the proof. We have the assumption command here, which we've been using a lot. The restate command, which we used a couple of times in this proof specifically when we want to change the names of variables. The recall command, that's when we want to recall an axiom. We did that for the Boolean axiom. We never use this part. It's just an axiom that allows you to state that anything is equal to itself. Sometimes you need to introduce equality in your argument, and so that's how you can do it. Then the synopsis command that allows you to step out from assumption blocks and make a summary of what you've proved after having assumed something. Then this application command that allows you to apply implications. Left substitution and right substitution, which we've encountered right at the beginning of looking at proofs, where you use equalities to substitute into formulas. And that's it. This last one is just for convenience when you're typing up the proof not in this interface, but in runtime. So you enter one line by line as you run the program. If you want to delete a line in a proof, you can use this command. So it will delete the previous line. Here it doesn't make sense to use it because we can just delete it just like that. You can just delete something, but sometimes you can't do that in Python. If you're running your, I don't know the terminology now, but if you're running your program like here, if I had been typing my commands here, right? When I move to the next line, I can't delete the previous line anymore. So if I want to delete the previous line of the proof, I would then use this. Mathematical logic that only requires these rules is called intuitionistic logic. In fact, a true intuitionistic logic is just a bit more than that, but it's going to be covered with the Boolean story I'm going to tell now. So you see that falsity doesn't appear here. So these are rules of logic which do not, which say nothing about falsity. And then we have a separate class, bool, as we looked the other day. And so let's get a help for that as well. I first have to, I can only call help with the Boolean object already introduced. So I have to put BL here. So this is Boolean axiom builder. It only has two commands. There are two types of axioms. So this returns an axiom that uses falsity. This axiom says that falsity implies anything. Let's say if I want to claim that blah blah xy implies anything for arbitrary values of x and y, I call this function and I will get that whenever I'm given x and y, then falsity will imply blah blah xy. And the double negation rule, which we've already used twice in this last proof. Now, together with these axioms, so these axioms together with these two are supposed to capture first order logic. So one of the things you can do, for example, with this is to define OR. You can define OR using falsity in the following way. If I want to say alpha is true or beta is true, I can say it like this, that alpha being false and beta being false at the same time is false. So that's how I can express OR in this language. It's a bit long, but it still works. Anything we need to know about OR or we do know about OR can be derived from these principles. And so in the end, we have this quite a remarkable thing that just these principles can be used to compute any type of mathematical proof. And moreover, reduce computation of the proof in such basic steps that computer is confirming whether there is a mistake or not. Okay. Does anyone want to ask any questions so far about what I just said in the last few minutes? If not, then the question is, where do we go from here? What's next?
Yes. Can I ask something?
Yes, please. Yes.
Actually, can you please go back? You just made an example on how to express and or. Is briefly explain yeah, just this logic.
What should I do here?
Can you please just express how are those two statements equivalent?
Yes, sure. Yes. Thank you for that question. So what does it mean that alpha or beta? What does that mean? That means that at least one of them must be true, right? When we say alpha or beta, we mean that either alpha is true or beta is true. At least one of them is true. So at least one of them being true is the same as both of them being false. So what I'm saying is that alpha or beta, now let me use standard mathematical notation. Alpha or beta is equivalent to not alpha and not beta being false.
Yeah, it's quite clear now.
Right. And so that's what we say here. And in terms of expressing and, we never discussed that, but that's quite obvious. So that's just this, putting the two statements together. By the way, talking about first order logic, in first order logic, we have these quantifiers. Let me show you how these are captured by Sophia. That's another simplification that Sophia does. You don't have to think of quantifiers as something separate anymore. So for every x alpha x, let's actually try to do this together. How would you express this? So in first order logic, this says for every x, alpha x is true. How do you think we should express this in Sophia? And this one, if you want to think about it, maybe the other one is easier for you. This one says there exists an x such that beta x is true. Let's make it more concrete. Let's say I want to say for every x, x plus 0 equals x. And here I want to say there exists x such that 1 times x equals 0. How will I say these two things in Sophia? We've been encountering them all the time in this proof. For example, if I go back to the statement of the theorem, it told me that something will happen for every line and every plane. Given a line, given a plane, something happens. What happens? A point exists. So when a variable is on the left side of the implication, that's the quantified variable by the universal quantifier for every. And when the variable is on the right side of the implication, it exists. So this one would be expressed like this. Given x, I can conclude that x plus 0. So I'm now using full Sophia syntax. So 0 is a constant. That's why we put it like that. X plus 0 equals x. Right? So this corresponds to that. And for this one, I don't need to be given anything. I'm just declaring that there exists x such that 1 times x equals 0. I hope I got the amount of brackets right there. A nice exercise would be for you to try to write down the definition of a limit, the epsilon delta definition you might have seen at some point using Sophia. So for every epsilon, there exists delta, such that for every x, and so on. Okay, so coming back to what I was saying earlier. By the way, does anyone want to ask anything here? Is it clear why this is a Sophia way of expressing that, and why this is a Sophia way of expressing that? Okay, so if nobody is asking, yes, please. There's a green tick. It's one of the participants, Francesco. Does it mean that they want to speak or not?
I don't know. I'm just stating that.
Sorry, sorry, I was muted. I was talking without unmuting. I think it's just a sign of approval. Yeah, but Mpumelelo can confirm. Huh?
Okay, thanks.
Is that?
You're muted. Could you please?
Yes, I'm stating that what Francisco said is true. I was just basically stating that, yeah, I do understand. I'm not sure about my fellow colleagues.
Mm-hmm. Okay, great. Thank you. Thank you. So the question is, where do we go from here? Sophia is, as I said at the beginning of these lectures, it's something that we are we started building in Stellenbosch. There are a few students involved in this project. For one of them, at least at this point, one of the goals of PhD studies of the student who is doing a joint PhD with Professor Alessandro Parmigiano in Netherlands, his goal will be to mathematically prove that Sophia fully captures first order logic, that anything that can be proved in first order logic can be proved in Sophia and vice versa. So this requires a mathematical proof, which is what he might work on. So there is this mathematical side to this, but then there is also computational side for future work. So at the moment, there are a few proof assistant software around the world. Some of them are quite famous, some of them are less famous. And what they do is that they help the user to enter proofs, not just confirming that what I entered is correct, which is at this point what Sophia is doing for us, but also in completing some steps. Like here, for example, imagine that I began my proof with this line, and then somewhere, let's go back here. So imagine I made this assumption, and then I want to skip and come to this directly, maybe. And I'll tell Sophia, look, I kind of know that I should be able to prove this in a few steps, but I'm too lazy to do that. Can you do it for me, please? Now, how can Sophia do something like that? If you look at each line of the proof is using one of the few deduction rules we have with suitable parameters. So she could simply loop over all possible parameters, basically, right? This might become too long process if now she needs to make predictions of what kind of assumptions to incorporate along the way. So computational complexity might quickly jump high. But at least in some cases, she should be able to complete the middle steps for us. And that's exactly what these proof assistant software do that is out there. But as you see from this, it's not difficult to implement that functionality. We just have to implement the functionality of looping over different sequences of deduction rules and looping over the parameters, right? So this functionality still needs to be added to Sophia. And if any one of you is interested to work on that with me and the others in the group, that will be fantastic. So just let me know, and we'll take you on the team. And once we add that functionality, then Sophia would become at the same level, hopefully, as other proof assistants out there. One thing that urged me to work on developing a new proof assistant rather than learning something that was out there was the incredible complexity of the things that are out there. For one of them, for example, the book manual was like 500 pages, I think. So the idea is that this is supposed to be more user-friendly. I mean, you cannot skip the mathematics. The mathematical challenge will be similar in all cases, but the language is supposed to be easier than for other proof assistants. Of course, this could be subjective. I mean, maybe someone else will find something else easier. Yes, please.
Just out of curiosity, can Sophia prove if a certain statement is unprovable? Can you
if certain statement, so if certain statement in Sophia is unprovable,
can solve like Sophia in a certain mathematical statement is unprovable?
So whatever you can prove in mathematics, you can prove in Sophia. It's just that if you're working at a certain level of logic and you want to prove something about that logic, you first need to create an instance of that logic at a lower level where you're going to work. You cannot prove something about, I mean, you cannot prove things. It's a bit like looking at myself. I cannot look at myself. I need to look at the reflection of myself in the mirror. So if I want to prove something is not provable, I would have to first create a mathematical theory inside which I'm able to carry out such proofs. This is how it's done in mathematics as well. So once I do that, then yes. But otherwise, might not be. I mean, there are many open problems in mathematics for which not only solution hasn't been found, but also we don't even know. Maybe it's not possible to find a solution. And usually, another thing to mention here is that mathematics relies on axioms, right? So when something is not provable, it means that these axioms are not enough. And to confirm that the axioms are not enough, you need to find a counterexample. But to find a counterexample, you need to move to a different axiom system, the axiom system in which you build examples. So theoretically, complexity will be very high. But Sophia can definitely prove because mathematics can prove, and whenever mathematics can prove, and so in that sense, Sophia cannot do anything less than mathematics can. So she can do everything that mathematics can do. But it's a good question. Yeah. Okay, so I think this is where I would like to end with just this open invitation. If anyone is interested to join on this project, they're very welcome to. Otherwise, thank you very much for participating. There will be one more quiz that will be put up today, the final quiz summarizing everything. And I see there is someone else who raised hand. Maybe we can give them a chance as well.
Thanks, Zurab. I have a question, but this question is more on a personal note than the lecture that you have been giving. I noticed you were somehow at some point writing on a electronic board or something. I just want to find out what kind of device do you use, and I see you use Paint. But what kind of device do you use? Because the reason why I'm asking is I sometimes also teach, and I find it difficult to teach online. So is it a notepad?
This is called a Wacom tablet.
Sorry, a what?
Wacom 1.
Okay.
Wacom, W-A-C-O-M. And it has a screen which shows you what's happening on the computer. So it has an HDMI connection. And there is a pen.
Okay.
And this one is the Paint software.
All right. Okay.
And it's something that the university got for me for online teaching. So that was nice. Very, very useful. Extremely useful.
Okay.
And then there is also a question on the chat. Where would one contact me if there is interesting to joining in the group? Well, my WhatsApp number was published on the Moodle of the module, but also you can contact me by email. So that's my email, and this is my number. So thank you, everyone. Thank you, Francesco, for this opportunity. Thank you to CHPC for the opportunity. This is where I end.
Yeah, Zurab, you don't have to thank us. We have to thank you because it was really an excellent set of lectures. Yeah, and I think we all learned a lot. And it would be really amazing to make this project one of the NITheP's open source project and make it become famous all over the world. So you have all our support, and we should maybe advertise it like this, so that we get maybe some of the young people that took part in the course to assist you in developing the software package. Yeah, that would be absolutely amazing. Yeah. No, thank you very much.
Yes, thank you. Thank you. Mm-hmm.
Yeah, I see there are lots of thank yous in the in the chat. I will send you later the file with all the thank yous. Yeah. So I think your lecture series was really well received, and we all learned something new and fascinating. So thank you very much for that. It was really nice. Thank you. Okay. Then let's end this morning section with the advert for this afternoon. Yeah, this afternoon at 2. Sorry, I've forgotten. We have again Dr. Mbata speaking about Python for the geosciences. Yeah, and so please join us there as well. And don't forget that tomorrow we still have a full day of lectures and our short closing ceremony after the last lecture of the school tomorrow afternoon. Yeah. So thank you very much again, everyone, in particular to Zurab. Thank you so much. We really appreciate that you kept going on with the lectures, although you're not at your best health-wise and just recovering from the famous virus. Yeah? So all the best for your recovery as well, Zurab. And we are looking forward to engage on another project very soon. Yeah. So thank you very much. We will see you soon again. Thank you very much to everyone, but I will see all the others this afternoon. Yeah. Thank you. Don't run away. Yeah. Thank you. Bye. Bye-bye. Have a good rest of the day. Thank you.